we obtained in Kyushu University, Japan. So, as we all know, engineering materials contain many kinds of material defects. And the larger the defect, the more it reduces the fatigue strength. The similar event can happen if we have quite small defects, but they are so close to each other that they begin to interact and they coalesce and form larger defect. Here is one example of elastic analysis. What happens to stress intensity factor in the case when the defects interact? So we see that when the defects get closer, the stress intensity factor is increased exponentially in some points. And all this analytical stuff has been summarized, and it's called a rule of thumb. It's it means that if we have two defects and we have enough space between two defects to put another defect which has the same size as the smaller one, then we don't have interaction between these two. But there is no yet experimental verification. So, objective of our research was to find a general rule for fatigue interaction. So we want to know, for a fatigue limit, do the two defects behave like isolated ones, or do they behave together like larger single defect? And when things get complicated, is that the fatigue limit is not defined from the crack initiation, but it's defined from the non-propagation of the cracks, which initiate from the initial defects. And when we have a cracks which initiate from the defects, stress intensity factors increase due to the another crack, but on the other hand, we have a crack closure which reduces effective stress intensity factor. So the final condition is the battle between crack closure and enhanced stress intensity factor due to interaction effect. And we need to predict fatigue limit, and we used the famous root area parameter model by Murakami and Endo. And based on these analytical findings, we defined the area in different ways depending on the distance between the defects. So if the defects were very close, we took into account the area of the bigger defects. If they are far, we took only the area of the larger one. And the material we used was medium Curtin steel with microstructure consists of perlite and ferrite. And the specimen we used was round specimen with 7 millimeter diameter, so it's very large compared to our defects. And the Vickers hardness of this material was 186, and the scatter was plus minus 5%. And we divided our experiments into two series. First we had same size defects, and we changed only the distance between these. And for reference, we also tested with only single defect. And another series consisted of also taking into account the size effect. And if the specimen survived till 10 million cycles, we considered it as a non-fake one. And in this table, I'd like to point out three things. One is that if we only look at the numbers, the difference is very small. But the behavior was completely different, as I will show you later. And another one is that we have a small scatter, like plus minus 10 megapascals approximately. Because, for example, here we have a higher fatigue limit for two defects than it is for a single. And third one is that when we have different size defects, the fatigue limit was always the same. And here we have non-propagating cracks on the fatigue limit. There is some misalignment due to real vibration, so we repeat this test, and I will show this a bit later. But anyway, we didn't have any kind of cracks on the fatigue limit. Here we don't have interaction, and we have a non-propagating crack also from this defect, and here is nothing. And In the case where we had a strong interaction, we drilled in total 8 holes in one specimen. And we have 3 different kind of cases. And this is very important effect of the microstructure, because we have a strong perlite here, and it seems that it prevented even crack initiation in this case, even though we have a very strong interaction. And this is for reference single defect. We had only 1 non-propagating cracks, a little bit strange shape, and 3 holes didn't have any cracks. But with 10 megapascal higher stress amplitude, the specimen failed. So this is our fatigue. And here we have different size defects, and here we can see clearly the interaction effect. Here the defects behave like a larger single defect from the beginning. And here we don't have any cracks. And we repeated this test for 5 megapascal higher stress amplitude for the specimen failed. So this is our fatigue. And in this case, the cracks clearly behave like a single ones. We have non-propagating crack here, and they behave. Here is nothing here. So they don't care about each other if they exist. And we have some small data due to local microstructure. This is when we had a misalignment due to vibration of the drill. We repeated this test, and this is a critical distance case. And after 5 million cycles, we have 1 case when we don't have any kind of cracks, and 1 case when we have 2 non-propagating cracks. And here we have 1, and here we have a coalesced whole pair, and eventually this specimen failed because of this coalesced one, but the life was quite long, almost 9 million cycles. So we considered this stress amplitude as a fatigue. And as a conclusions, so 2 defects behave always like a larger single defect when the distance is smaller than the critical distance. And on the other hand, they behave like isolated single defects when the distance is larger than the critical distance. And the interaction effect becomes unstable on the critical distance, but the analytical critical distance holds. And as we saw, the local microstructure has definite effect on all kind of crack behavior and non-propagating crack characteristics. And if we have unequal size defects, it seems that the larger defect alone determines the fatigue limit.